So everybody said it couldn't be done. I've been battering away at this for 10 years and more, and it's only when you get there that you realise what it is. I woke up the following morning just bouncing with excitement. We'd lifted the bridge, and I was full of ideas about how we could make it cheaper and quicker and better and things like that. But there was another excitement, and that was before we left the night before, I took some photographs, and here, for the first time ever, an engineer gets an X-ray of a bridge, can actually look inside. This is a slice through the abutment. It's 2 photographs. There's a jack in the middle, there's 2 jacks each side, slice straight through, and the bricks are just laid out as if in a stack. No mortar in the per hinge joints, no bonding of the brickwork, just straight lines straight through. Now, there's a sense in which we all knew that, but it's on record. We'll see some more of that as the evening goes on. These days, you can put those models into those photographs into a 3D model and actually get a proper plan view, and then you find interesting things like the back face of the abutment isn't parallel to the front face, so if you set the jacks out from the back face, you find you're going in on the squint, and that's an interesting thing as well. However, let's go back to square one. What's it all about? The basic problem is that the pantographs won't go under the bridges. Well, the power lines won't go under the bridges either, but it's not just the power lines in the middle, it's the pantographs at the edge that would just be taken off as the train goes under the bridge. And there's an array of possibilities for dealing with it, and one is to knock down a perfectly nice brick bridge and put in what to me is a perfectly nasty concrete bridge to replace it. Or you can do the other thing, which is to dig the track down underneath the bridge. Unfortunately, quite often if you do that, it then gets a bit soggy in the bottom, and it's also quite expensive because you have to dig for a long way to produce a gentle enough ramp down and back up again. So we could lower the track, 300 metre slope each side, wet patch in the bottom. There's talk of the possibility of insulating the bridge so we can get everything up a little bit tighter, but it's still a bit tricky. There was an innovation competition. I was a bit miffed about this because I'd been battering at Network Rail for at least 5 years about the possibility of lifting them, and I only heard about the competition the day before it closed. Got to an initial meeting, took along my little model to say, look, all you need to do is pick it up in the right place and it just picks up. Those are independent blocks. I couldn't bring them with me because it's just too much stuff and too much fiddling, but they do pick up just like that. If you pick them up in the right place, the whole thing just stays together. I met Graham from Freyssinet, who said, that's the sort of thing we could do, let's see if anyone's interested. And they bought in and we entered the competition and got there. So the basic scheme is to contain the thrust, cut the arch free, and lift it. Easy. Really? Just contain the thrust, cut the arch free, lift it up. Yeah. It's a bit more complex. So a desk study to start with. Go through the whole design process, discuss it with the various contractors and everything else and make sure it can be done. Get to a proof of concept and get buy-in from partners and from Network Rail. That work was all done on the Midland Main Line on a bridge called OB49. There was 9 months of work to get us into phase 2. Phase 2 was a demonstration project. Yes, well, never mind. Let's draw a veil over that. Now we're on to overbridge 14 at Moco Farm on the line from Bletchley to Bicester. Yes, Bicester. Question 1, is it suitable? Could it be done? Well, let's have a look. First thing you do is go and look at the bridge. And there are all sorts of interesting things just going and looking at a bridge. So, for example, I hope that you can see there's the step where the parapet just nudges 40 millimetres over the edge of the spandrel wall. That makes it good and strong, doesn't it? But it's a standard sort of feature. Down from that, so running down tangentially from the crown of the arch and at a slightly steeper slope, there's a distinct change in brickwork colour, which is something going on behind, and you need to notice it if you're inspecting bridges. A bit further down, if you look closely, you'll see that there's an area where the quality of the brick changes. Above the line, it's badly pock-marked. Below the line, it's in good condition. There are two possibilities there. It may be that, again, there's a change in what's going on behind, or it may be that it's been reskinned. And I will say a little more about papering over the cracks later. Well, in fact, I'll maybe say a bit more about papering over the cracks now. This is what we mean by reskinning. You hack off the outer half brick and you replace it with something new. Of course, you don't stress it into place or anything like that. You just build it up to cover it up. You just paper over the cracks. And in this case, there was a crack, as you can see in that left-hand picture, wandering up the face of the bridge. Looking a little closer at the spandrel and wing wall, I think you can see what I mean about that whole area of pockmarked brick, and then you get into an area where it's in better quality. And I think generally those are original bricks. Not all of them, but I think most of them are original bricks. So it's almost certainly a sign of something different going on behind. What else is there to see there? Well, there is the fact, which isn't entirely visible, but at the springing level, the beds are horizontal, and by the time you get to the bottom of the parapet, they're sloping with the parapet. So the brick beds are doing that as you go up the side. That makes life interesting, and you're trying to work out what's going on. If we look underneath, you get the classic black band where the steam used to hit the bridge, and the acid from the smoke took all the mortar out. So you've got a band there, and a band at the left, band at the right, with mortar just about gone, band through the middle with the mortar in perfect condition. As it happens, the middle is where you're most concerned about it, so it's probably a good idea. Cracks. There's a vertical crack through the abutment at the right-hand side of each face. In other words, in diagonally opposite corners. And I still haven't worked out why. But it's there on more than one bridge on this line. Diagonally opposite corners, just like this. But it's not a bad crack, is it? It's, you can't get your finger in, it's not really serious. This is, as it happens, an accommodation bridge, and I didn't mention the fact that, of course, it's across a railway line that's closed, so we're not getting into any difficulty about possession work or anything like that. We can actually just get on with the job in hand and lift it. I keep saying we. By this time, we is Freyssinet. Let's be absolutely clear about this. Without Freyssinet, none of this happens. So we've got a nice ramp up and over the top, just a dirt road, bouncy tractors going over it, but nothing else. But of course, tractor loads are actually quite big these days, aren't they? Just one more shot of the underneath, partly to demonstrate the sort of thing you can do with modern cameras. That's a Canon EOS camera with a 14mm lens on a full frame camera, so that's just a single shot looking at the whole thing. And we even have a drawing, but it takes a second to load. Of course, it's been microfilmed and probably digitized from the microfilm, so the quality has gone down somewhat, but you can see quite a lot about what's going on. Interesting features. The abutment foundation is just a foot below the foundation, the formation of the railway. Not a lot. The wing wall foundation is a similar distance below existing ground level, which is rather higher. So there's a step up to the wing walls. But despite the fact that the wing walls disappear into an embankment, the foundation is horizontal. That's normal as well. In a cutting, they would be stepped upwards. But in made ground like this, the foundation is always straight into the original ground, and that's at least partly because the bridges were built first, and building them with a big overhang on the back was quite tricky. The little bit of handwritten stuff in the bottom corner here we'll come to in a minute. Move. So, an elevation which shows the slope and the rounded crown, and a plan showing the sections that the wing walls taper away as you get towards the back. A section through which says that the abutment goes up with a flat back to a little below the crown of the arch and then horizontally at the top. And you can see vertical lines in the wing walls which show where those tapers are, and they appear to go right up to a line which marks the top of the thick part of the wall. Drawings like white man speak with forked tongue. And we have a section which shows that the walls get a little bit thicker just immediately under the ground, and then quite a lot thicker, and then they go right down at constant thickness. And here we get to the fun bit. I know it's almost illegible. I have spent some time working at it. It says 463 cubic yards of brickwork, £509 and 6 shillings. Just imagine, yeah? 210 cubic yards of, linear feet of coping stone, 588 super yards of metalling, so the road surfacing, 73 quid, so 10% of the price of the bridge was just the road surfacing. Another 10% for fencing, 497 linear yards of timber fencing, 2 field gates, £10, £5 each for the gates. 20 yards super of clay puddle, so that's a puddle clay 9 inches thick, 20 square yards of it, for £1, 5 shillings? Just mind-boggling. Anyway, a useful and slightly distracting bit of information. So we took a load of photographs and made a model, and because some people are watching this on their screens, and I think this isn't going to work on their screens the same as it does on mine, I've given that link, and I hope that FPUFSX is short enough to type in, and you can look for yourselves while I try and entertain people here with a 3D model of the bridge made from the odd 1,000 photographs, which allows us to do that. And if I could work out how to zoom, I would zoom as well, but I'm not sure that... Can I do it? Yes, I can do it like that, yeah? So you can zoom in, you can rotate, you can examine, and you've got a complete detailed record. And really, it's long past time we had that for every bridge. So it's not perfect, but it's sort of good enough. Yeah, we think we can do it. Let's give it a go. What are we going to do? We're going to cut, and the original plan was a vertical cut down through the abutment, horizontal cut just below the springing, bearings in slots down the back, jacks underneath, pick it up, and this is where things get interesting because I'm not sure this slide moves on, but obviously the arch produces thrust, and it normally has a reaction there, but we have to change into 2 separate reactions and deal with them independently. What that does effectively is put a hinge at each end. So your fixed arch has become a 2-hinged arch. Not a 3-hinge arch, a 2-hinge arch. And provided you don't let the span change too much, it will remain a 2-hinge arch and remain really very stable. Even if you let it crack, it's going to be okay, but you can stop it cracking, keep the thrust fairly close to the centre of the ring depth at the crown, and it will be fine. I think there's... Oh yes, perhaps we ought to mention the fact we've got some patents on the idea. Now up the sides, some soldiers, just to make sure the cut ends of the parapets don't get knocked off while we're messing about with the rest of it. There's a fair amount of reinforcement went in. I think we can probably do without quite a lot of that. And then jack it up, put in some barrels, fill them with grout, take the weight, finish off the brickwork, and away we go. The jacks we used were new things from Enerpac with, it's going to decide to keep moving on. I killed this several times and it just keeps deciding to go again. They have a square base. The idea is that they lift from the top, the ram pushes downwards and you put eckie timbers under the sides. So you lift it up 100 mil, put a couple of timbers in, pull the ram back, put some more timbers in, push it up again, timbers again. But the loads we were putting on were sufficiently below the full capacity of the jack that we were actually able to load on the bottom of the shoulder. And obviously the lower you can lift from within a block, the better the result is likely to be. We had to do a load test before we started, and yes, I have got a pointer, haven't I? So I don't need to keep going over there. Oh, wait, whoa, go back. Is that the one? That's the one. So down here we've got a graph of deflection as this thing went over. You can see the front axle and back axle of the tractor, and then the heavy load of the trailer, about 20 tons in the trailer, quite a lot of which was on the back axle. Total deflection about 1.5 millimeters. Not a lot. And then we have to start work. The first thing, of course, is to put in a diversion for the farmer so he can get round the bottom. I'm sorry, I'm going to have to fight with this now for the rest of the evening, I think. A road round for him to get his cattle round while the work was going on. Well, it's the first time, so let's dig out and have a look, and what we find is that it does indeed get thicker, not far down, but not as thick as they said it was going to. And we haven't quite found the abutment yet, but it is there really. But what we have found is when we get down to the abutment is that the crack, which was like fingernail thickness on the outside face, is fist thickness at the back of the abutment. Now that doesn't show on the outside, right? That 3D model, the outsides are vertical and plumb and straight. So in the course of hacking off the face and reskinning it, the bricklayers naturally used a plumb bob and brought it up straight, and not only did they disguise the crack by papering over it, they also remodeled the face so it was vertical, so there was no other way you were going to find out that there was anything nasty going on in there. Well, we did try to grout that, as you might imagine. But also because of those cracks, we put a little bit of reinforcement across the crown, just to give us that sort of little bit of comfort that it wasn't going to split in half in the middle and fall off sideways. And then some reinforcement down into the abutment, into the top of the abutment, to hold it all together. And I'm just going to have to keep clicking back on this. How many times do you have to take this out of PowerPoint? Dig down behind the abutment, because we had to work in there, because the idea was we weren't going to work on the railway. And there's a slab across the top just to provide a bit of protection for people who are working 5 metres down that hole. There's that crack again, slowly being grouted up, and the holes appearing in the side to put the bearings in. And I think I'm going to skip over that model and come back to it. Now here's the lines I was talking about earlier. So according to the drawing, this step, just talk among yourselves for a moment, sorry. Well, we can see it there anyway. According to the drawing, this step is at this level. So you can't entirely believe the drawing. I mean, it's perfectly sound from an engineering point of view, but on the other hand, we're moving the thrust of the arch up, and most of it's going to go on those wing walls, and finding that they're getting thinner at the top wasn't entirely encouraging. It's always useful in places like this to label everything up so you know where you are. When you get down in these holes, you can't always be absolutely sure which side you are or which end. Yeah. And now I'm wondering whether I've skipped over it. Yes, I have skipped over slides that we need to look at. So I've already said about the step there. Here we are cutting cores into the brickwork, and what we saw in that first photograph is emphasised by what came out of the cores, that the bricks are in fairly random orientation. No, they're not. They're flat, but they're not laid out in any bonded fashion. There's no attempt to fill the perpends with mortar. Some of them are frogged down. So it's definitely rough and ready masonry inside the structure. And you can see that here when you start to take cores out and look up through the section, that there are all sorts of gaps there as well. And this was to put a vertical sliding bearing, so the thrust comes through here. Behind that 400mm high steel plate, there's a 150 high piece of PTFE, so it is actually a sort of hinge, and then the whole thing slides up against this plate. In the end, we cut very slightly diagonally because we weren't absolutely sure it was going to stay clean and wouldn't jam on the way up lifting. So as we lifted, it came clean, and we were confident it would come clean. I think we would certainly be happy to cut at a steeper angle. I'm not sure whether we would wish to go absolutely vertical, but we'd certainly be prepared to cut much steeper than that now. Anything else there? No, I don't think there's anything else there. We've already jumped as far as that one, so maybe it's time to look at the jacks again. So I think that's a 400 square plate with the jack in the middle. There's a pad at each corner. You'll see why that is in a minute or two. The ram pushes downwards, lifts everything upwards above it. At the moment, or at the time this photograph was taken, the cut had been put through here and the whole bridge was sitting on 6mm strips of steel that had been jammed into the crack. And here it is ready to go, and now I want to divert just briefly onto other parts of our business, because across here we have carbon fibre poles with deflection gauges at the end of them. There's a deflection gauge coming out of the bottom of the box here just to tell us whether we're going up or down, and there are also gauges measuring side sway as we go up the corner bearings, and they were all definitely part of the Harvey business. Once it's up, you can start to see how it all works. So the Jenga underneath, you put a block of wood each side when it's sitting on the ram, retract the ram, put 2 blocks in the middle and a piece of steel on top of them, and then push the ram up again and put 2 more blocks in, and just go up in 120mm steps. It's wonderful, very effective, very straightforward. Working out how to do this was quite interesting, fairly time limited, especially on time to rig the equipment. So this is a little potentiometer connected to one of our loggers. There's a piece of aluminium strip stuck onto the side of the vertical bearing. This is with the bearing right at the top. This piece is held onto the sliding part of the bearing just with magnets, and it's measuring displacement of that side against that side as we go up. And maybe I can risk instant death by switching away from here and looking at something else. Sorry, I need to be back there, don't I? I need to close that and find a slightly different website, which is this one. And we should find that that is measuring deflection between the floor and the table with a bit of luck. Yeah, there it goes, look. At the right hand end of the picture, as the graph comes across, you can see as I walk on there, just my weight on the floor is enough to record it. This lot comes up on a website, can handle up to 8 gauges at a time, and was also modified to do the testing, the load tests, and long-term monitoring of the bridge during the lift, or during the preparations for the lift. So, for example, when we cut the arch out, cut it free, we wanted to be sure the span didn't change noticeably. We wanted to be sure it wasn't creeping while things were going on. So measure everything all the time is always a good motto, I think. And at the same time, we set up a box with a mast to pull us into the 4G network and broadcast a Wi-Fi which was available to everyone on site. So everybody on site could see the results of the measurement as they came in. And here they are. So now we start to get to the technical bit. So on the screen of an iPad or a phone, you get a dashboard like this. This is lift against time. So it sits still for a while, it goes up fairly quickly in about 5 minutes, the 120 millimetres, sits there while the timbers are put in, down onto the timbers, and then sits there while all sorts of measurements are done to make sure everything's gone that 120 without any trouble. The right hand is just a block saying where we've actually got to. Then down here we've got change of span and left and right movement. The top one is just the instantaneous value, and you can see one span is changing one way and one span is changing the other, which is not necessarily entirely what you're hoping for. Even more interesting is that in the side sway, one end is moving in one direction, one end is moving the other. The graph underneath is against lift, so it tells you where you are this way and how it's moved this way against that, and then below is time against movement, so we can see how the movement goes like that. We're almost certain that what was going on here was that the west side of the bridge, one of the bearings was inclined very, very slightly. So the span was getting squeezed on that side, and by squeezing on one corner, then the whole bridge was inclined to twist as it went upwards. And what doesn't show on this particular picture, but did show later, was that it goes up and twists, but as it comes down, it comes back out of the twist again. But just an indication of the level of control it's possible to have, that you can know exactly where your bridge is at any time, instantaneously. Anyone on the site can have it. You just log in and pick it up on the iPad, or even phone, in fact, and see what's happening. And now I'm back to my bridge engineer mode and looking at the cross-section through the wing wall and saying what good quality masonry it is. I guess it's what you get for, what was it, £500 for 400 cubic metres of brickwork. There's a limit to the quality you can buy for a given pound, I think. This is looking upwards at the cut face, and you can see here how the jacks are set in, grouted into place, and then there's the pile of Jenga underneath. And there's the pile with the whole thing actually standing on its rams waiting for. Actually, that's not, I think, waiting for the last pile. Just to complicate matters, the original discussion was to go just over 400 millimetres with this lift. And having designed the whole thing to do that, then someone came along and said, well, just occasionally we like to go rather more than that. Could you take it up to 900 and then back down to 400 just to show it can be done? Yeah, why not? Yes. We have got a week to work it out and make it happen. Anyway, we went up, the last 100 mil, we just went up on the rams and came back down again. We didn't put the Jenga in at that point. And I think at the end, I can't remember properly, but I think at the end of the day it was actually left up at this level and then brought down the following day. And here's yet another section through the brickwork, but you can see here what I mean about reskinning. No connection whatsoever between that skin and the core brickwork. Just hacked off and a new skin put on. But if you look at the quality of the brickwork inside, which bits did the bricklayers think were the structural bits? The bits that we just glibly hack off and replace without stressing them back in. And, is that ideal? Here we are, a bridge up in the air, and no sign of a crack, no sign of a tilt, nothing. So you can't just put the ram on the eckie. Indeed, you can't even put these pads on. You need a bit of a steel pack for that, but the ram has to have a fairly substantial pad to spread the load out. I'm not sure I want to put my fingers in there. It's not good policy, is it? Really? And now we've got a bridge which is 900 millimetres up in the air. And it's perfectly happy. It really doesn't care at all. Here's a whole array of little bits and pieces of bars doing different jobs, holding everything together. This, I think, is a camera, so we're able to watch some of the detail. But one obvious problem is the step in that step. There's a little step at the bottom of the parapet, and you've got a 900 millimetre step in it at this stage. We do reduce it rather from there. So here's the pile of Jenga. We put in a block under each side to take the weight, pull the ram back, put those two in, steel plate on top, push it up again to this level, put in another pack, and away you go. It takes time because there's 5 of them and the lumps of wood are big and they're quite heavy, and some of them are quite a long reach underneath. So it maybe takes 10 minutes to pack all that in, and that's one of the places that I'm sure that with a little bit of further thought we can take a chunk of time out of it. Yet another shot of the underside of that cut face. You can see the sweep here where the diamond wire went through. It's really a remarkably good process. Very effective, fairly quick, relatively easy to set up, fairly clean finish. And the great advantage is that although we've cut right through these bricks, the bricks haven't been disturbed enough to fall out, and they're clearly only held by the mortar on top. And that's maybe a point worth making as well. People get very agitated about lime mortar that has no tensile strength. It doesn't have no tensile strength. It has a very small tensile strength, which you wouldn't want to rely on as part of a structure. But actually it's capable of hanging about 4 metres of brick. If you fill each layer all the way down, the strength that you're talking about is capable of suspending about 4 metres of brick. So holding in the odd brick over a metre a span isn't hard. Builders have known that for a long time. Builders have no trouble putting needles through every metre and just taking away the wall. They don't worry about it at all. Bridge engineers get all agitated about cutting holes in bridges. A slightly more distant view of the holes in the side here and the ram going up. And this is way out of place, sorry. 5 cores for the jacks to go in. So 3 in a row horizontally to take the flange, 2 vertically for the ram to go in, slide it in there and then grout it into place to take the weight. And we're then taking the weight at this level, and if we cut at this level, everything that's being lifted is on top of the jack. We're not trying to drag too much up behind us. And that is out of place, isn't it? Just bars going into the abutment there to reinforce it. And this was the sort of gobsmacking view when it was finished. At the end of the day, when all the tourists had gone, to walk round the back of the abutment and think, I'm just going to have a gosh. That's a big hole. I can see right through. There really is a bridge flying in the air. It was quite a thing, quite a moment. Oh, that's quite interesting, isn't it? Yeah? Not only are they not, as shown on the drawing, they're not even the same across the width of the bridge. Well, it's all done in a bit of a hurry. I think I've probably laboured that point enough, but now I have got a pointer. You can see what I'm saying about these lines going straight through, just not broken at all. And I suspect they joggled the odd half brick on the way up, but it's only the odd half brick, so there really isn't much in the way of bonding in that brickwork. It's not much more than a stack of bricks. And here we are at the end of the day with a bridge that's a metre higher than it used to be, and standing there we have no doubt we can get our power lines underneath, which is good. Of course the job's not done, is it? We have to hold it up there somehow. Where did that go? There we are. These are pieces of drain pipe because the grout bags wouldn't stand that high, with grout bags filled up to close the gap and take the weight, so the jacks can be taken out and cleaned up. That's the finish on top, and another reason why we put the concrete slab on was that was going to be the finished road level, because it needed to go down as far as possible to minimise the additional rise over the crown. Notice how high the parapets are as you get towards the back here, and then there's a step down to the originals. A section through the parapet, neatly cut, shows that it's built at least as well as the wing wall was. And when we're finished, we find a source of second-hand bricks that look pretty much the same as the ones that came out, and build it back in brickwork. And one of the things you think about when you're doing stuff like this is just to remember how thick a brick is and lift it in brick courses, because otherwise you're going to make a whole lot of work reconnecting everything. One of our telltales across one of those nasty cracks, just demonstrating that it hasn't moved enough to even think about in the course of all that work, which is quite a nice thing. And there we have a finished bridge, 437 millimetres above where it started. And you really, I mean, you can see the join, but you actually only see it if you knew it was there, I think. I think if you were to walk along, you probably wouldn't see it. Step back and see the whole thing. There's enough patching in there anyway that the little bit of extra doesn't really show. One problem that did arise is that because these courses are inclined and fanning, the four corners aren't identical. So on one corner, the course was out of line, and there was a bit of fudging to do to get the bricks in. So the bridge was level, but the courses didn't line up, so we couldn't just slot the bricks in. And there's a picture before and after. It's actually from the opposite side. I couldn't find one from the same side, but bridge lifted. I'd like to say thanks to Freyssinet for doing it. There's something very special about people accepting what you say and doing it when it's something that a lot of people are saying can't be done. And yeah, it's something that I want to acknowledge and simply say that demolition is just so 20th century. Let's do better than that. There's a few links if you want to ask questions. There's an email. The whole bridge model is there on the web. You can look at it. There's a model which I skipped over, which has just the back of the abutment and the crack, which was made from mobile phone photographs. I think you took those, didn't you, John? John Kennels from Freyssinet. We rang him up on site and said, when he showed us that crack, can you take a load of photographs with your phone? And we made a 3D model of that, which actually, if I've given you enough time to look at that, the hidden defects note, let's say that. I was asked to do a talk at the introductory conference on the hidden defects book that's just been published by Syria. I couldn't go. Hamish went and did the talk, and as preparation for that, produced a really rather elegant note on hidden defects in arch bridges, and it's there to download. But we do ask you to sign up to be contacted before you do it. And if I do this again, I think that we may be able to get to the model of the abutment. There we go. So that one was made just with mobile phone photographs. And really, it's pretty good, I think. And you've got to say, very much better than one or two photographs. Yeah. It would have been very expensive for me to get in the car or get on the train and drive up to the bridge just to look. John was able to take a couple of dozen photographs, email them straight from his phone to Hamish. Hamish processed them and produced this model, and I can pretty much be there, actually see what's going on. And the value of that is, I think, just remarkable. You wouldn't think that I love technology, would you? But I think that'll do for now. Thanks.
Well, Bill, that was absolutely fantastic. Thank you very much. We've got some time for questions. Who would like to set the ball rolling? And there's a microphone that's on its way down if you do. Okay, Andy.
Thank you. Just looking at that picture, Bill, does that show correctly that the crack that ran back from the from the arch lines up with the thickening of the wing wall lower down?
Yes,
Yeah.
more or less.
Yeah. And so is the supposition that those cracks formed because of the pressure of the fill on the wing walls after the bridge was built?
There are so many possibilities, aren't there? I mean, that's clearly a possibility, although even just nib together half a brick with a reasonable amount of mortar in, the strength to pull that apart, getting that from soil pressure is quite demanding. I mean, it is possible, clearly, but it's quite a lot to ask. I haven't at all got my head round what caused those cracks yet. I certainly haven't got my head round why you would get them in diagonally opposite corners on more than one bridge.
Yeah. But it appears there to taper down.
It tapers
from the abutment up towards the crown.
Yes, it does taper. It disappears at about the third point of the span, and then starts again the other side at the opposite third.
Yeah, yeah. And can I ask a supplementary question, Richard? How with the vertically sliding bearings?
Yes.
How difficult is it to set them sufficiently accurately vertical? And how do you know that you've got a thrust in the arch that goes roughly through the middle of the crown, which you said was desirable?
It's desirable. It wouldn't be the end of the world if the arch cracked, but obviously we'd prefer it not to. It will take about 0.5 millimetre each way without cracking. And that's not to say you're going to get a significant crack. I'm saying without cracking at all, it will take about 0.5 millimetre each way. So the precision required isn't actually that great. I think it was a bit of a pest getting those in, wasn't it, guys? Was there some nodding back there? Yeah? I think it was quite tricky getting the bearings in and getting them plumb. And of course...
Get the bearings in, but getting them plumb wasn't so difficult. That screw thread adjustment on the top.
Okay, yeah, so the top plate had a screw which allowed it to be tilted, and provided you've got a precise enough plumb bob or level against it, then you can bring it to the vertical.
But before it was grouted?
Before it's grouted in, yeah.
Another question. Gentleman back there.
Yes, with respect to that containing the thrust, would it have been possible to sort of grout in a tie rod going from side to side to contain the thrust? Or?
Yes, but I mean, we did actually have tie rods in because we weren't absolutely confident. No, we were confident, but not everybody was confident that the wing walls would take it. Right, the combination, a little bit of friction in the lift offered that possibility of just producing a bit of a crack in that rough and ready brickwork and sliding the wing wall off. So there were two tie bars in to hold the thrust if anything broke. But they would have stretched 14 millimetres before they took it, and they were stretched to start with. So one of the issues is stiffness. That getting a stiff enough tie bar is very hard. In fact, the only way to do it sensibly is to put a strut and then tension against the strut, so you've got a decent area of metal taking the load.
And just quickly, were you able to measure the thrust, and did it sort of match what the theory said it would be?
We weren't able to measure the thrust. We could measure the weight, and that was within 10%. I wouldn't like to say more accurately than that, but within 10% of what we'd said.
Was that because the mortar joints were missing in the brickwork?
Well, it could be, couldn't it? Yes. It is just possible, yes. But you know, you're starting off from a guess anyway. You know, what's the density of this stuff? And one of the things that people say, how many bricks should I test to know how strong the brick is in this bridge? Well, you're going to have a factor of 10 difference in strength between one brick and another. So you would certainly need to test like 1,000 of them to get a statistically valid sample. So why bother? Yeah, just make a reasonable stab at it and have a look at how much difference it makes if you've got it wrong. And actually, it's going to weigh around 18 kilonewtons a cubic metre. It might be 20, it might be 16. 10% isn't going to matter. And the same is really true of the thrust. The thrust is dead load. Because one of the imponderables is that those parapets and wing walls are part of the structure. Yeah? Unavoidably part of the structure. So if you allowed the arch to spread, the thrust would for sure go up the parapet some distance before things started to flake off. So measuring the thrust would have been extremely difficult, quite expensive, and really not worthwhile.